We are going to talk today about thermally direct circulations and thermally indirect circulations, which is really nothing more than a conversion of potential into kinetic energy and back. So we are going to start here by showing you this. We're going to look over here and say we have a box and it's got potential energy. And the formula for potential energy, so potential energy, is going to be mass, the mass of this object, times gravity, which is really an acceleration. It's being, the Earth is accelerating objects to come toward the center of the Earth, times z. Z is the height above the ground. So if this is the ground, how high above the ground is this? And the first question I would ask you is, well, where is the box? Is it the bottom of the box? Is it the top of the box? Is it somewhere else? Exactly where is this box? Well, we create what's known as a little point, and that's called the center of mass. Now, it can be called the center of weight, the center of mass, the center of gravity, something along those lines. What we're basically saying is that anytime you have any line that goes through that center, whether it's this one or even any sort of a diagonal line, when I look at the line separates half the mass from the other half the mass. So no matter where I am in this box, I've got half the mass on either side of the line. And that means that our center of mass is going to be right there at where all those lines intersect. That's the center of mass. Okay, so I can get rid of all those lines and say there's the center of mass. It is from the center of mass that we define the potential energy. So that is Z. Now what happens when I drop this box and let it come crashing to the ground? And it doesn't have to be crashing to the ground, it can just be on the ground. Well, what we end up going to do is we're going to say, all right, well, the box is, ooh, that's not a box, this is a box. The box is now going to be here. And the center of mass of the box is still in the middle there. But do you see that the center of mass is still above the ground? So does this box still have potential energy? Is there a mass? Yes. Is there gravity acting on it? Yes. Is the center of mass above the ground? Yes. But I can't do anything else. This box won't go any further closer to the ground. So what we're saying is it has potential energy, but no available I can't spell available potential energy. Now you've heard of APE before when we put the C in front of it, and that's CAPE, convective available potential energy. Now, if the box could be crushed when it gets to the ground so that it's thin like this, do you agree that the center of mass can be moved down? But you're deforming the box. So outside of that, the center of mass still exists above the surface, but I can't do anything with it. Now, what do I mean, do anything with it? Well, what is going on when I drop this box? The box starts to go faster and faster, gravity pulls it down, and what I'm acquiring is kinetic energy. The energy of motion. And kinetic energy's formula is 1/2 mv squared, velocity squared. So as this box falls, I am converting potential energy. Potential energy gets converted into kinetic energy. Okay, so that's what I mean by this convert. Now, how does potential get converted into kinetic energy? The key part to say is by lowering the center of mass. That's how potential energy is converted to kinetic energy. Now imagine that I had, instead of a box, maybe I had a ball, a rubber ball of some sort. This ball is going to fall, Now when it gets to the ground, it starts to bounce and it comes back up, but it never goes back all the way up. It keeps going up and down until it finally goes and comes to rest. So what I'm saying is when the ball comes down, the center of mass is converting potential to kinetic. When it comes back up, the kinetic is being converted to potential energy, but never as much. It's not that we can do this perfectly. So the potential goes to kinetic, goes back to potential, and goes back and forth until eventually the ball comes to rest. So it had potential energy to start, and now it has none, at least no APE. It developed kinetic energy, but it also came to rest. So I had energy, but now it's not. Well, the laws of thermodynamics say that potential energy plus kinetic energy plus something else must always be constant. You can't destroy or create energy. You can transfer it. So where does it get transferred to? Well, a couple things. If I drop something, you may hear that I'm dropping something. I just want to make sure, okay, we do have a picture here, so. Okay, we are hearing it. That is the molecules of air moving. It's called sound. And it takes energy to move the molecules. So some of the energy of this falling object is converted to sound. And that's true to some extent. But the most important thing is it gets warmer. It goes to what we call internal energy, which is temperature. Or, if you rather, theta, potential temperature, which is a measure of heat. So in other words, the ball hits the ground and it's getting slightly warmer. The ball and the ground get slightly warmer. Okay, not very much. Now, if this is a meteor hitting the ground, it's going really fast. It can get really hot and things explode. So it can be important if it's moving really fast. Dropping a ball on the ground is not going to do much. But the key thing to realize is that the total energy doesn't change. So if we lose these two guys, it's going to go to internal energy, which is known as temperature. Okay? Or it's a function of temperature. Now imagine that we have a container, and in this container are some fluids. And remember that a fluid is something that flows. So we have a container like this, like this, like this. The only thing is in this container, I'm going to create a little partition. I'm going to put a partition in here to separate one side from the other. And on the left side, we have stuff that is less dense. And on the other side, it is more dense. Now, this box full of fluid has potential energy. And the question is, well, how much? Where's the center of mass? Well, I think it's pretty obvious that the center of mass will be something like on this line. Half the mass is above it, half the mass is below it. But left and right, it's not centered because I've got less dense. So I've got less mass in that half a box than over here on this side. So rather than being in the center, it's probably going to be shifted over here someplace so that this dot becomes the center of mass. It's all the, some of the dense material is to the right, some of the dense, a little bit of the dense, and all the less dense stuff is to the left. And that's where the center of mass is. So that means that the potential energy, or at least the available potential energy, is mass times gravity times that height, indicated by that green arrow. Okay, beautiful. Now, what happens when I remove the partition? So here we go. I'm going to remove the partition. I got the arrow. What happens to this fluid? Well, less dense things want to go on top. So think of this as oil, and this is vinegar. And you could shake it up and mix it, but then it would settle and separate out. So I'm kind of going to the ending idea. So I'm going to take this less dense stuff, and the less dense stuff is going to go up on top of the more dense stuff. And this more dense stuff is going to come down underneath the less dense stuff. Now, do you agree I've got some density here that's different than the density here? That's a density gradient. And a density gradient results in vorticity. Anytime I've got a shelf cloud, I've got an outflow boundary, I have a density gradient which results in vorticity. It starts spinning around. It will eventually come to rest. Let's do this. Like this. Where the less dense stuff goes up on top and the more dense stuff is down here on the bottom. And it comes to rest if you think about that. Now, how does it get there? Well, it's going to go back and forth like this. It's really what we call sloshing. It sloshes back and forth, just like if you took water in a bowl. There's water in there, it moves back and forth like that. So it comes down, potential is converted to kinetic, and then kinetic goes back to potential as it comes up, and back and forth, and eventually comes to rest. What's happened? It got slightly warmer. But the question is, where's the center of mass? Well, the center of mass is now going to be fairly much straight across the box. Probably didn't need an arrow, I probably just wanted a line. It's going to split the box up and down in half. But what about this way? I'm sorry, let me rephrase that. It's going to be left and right. I'll have the same amount on the left and the right, but since there's less dense stuff on top, the center of mass is going to be displaced not halfway, but further down. Sorry, I was a little carried away there, got a little excited about that. So the center of mass has done this, it's moved down. Now, we don't care that it moved left to right, that doesn't affect anything for us. But the center of mass has dropped. In doing so, potential energy got converted to kinetic energy. I said it sloshed so that it came back to potential, back to kinetic, back and forth until eventually comes to rest. Well, what caused it to rest is something known as viscosity. The fact that the air or the fluids or whatever you want to say resists motion. So it's like friction, eventually slows it down. Now, I have potential energy, but I have no more available potential energy. So what this is potential energy was converted to kinetic energy by lowering the center of mass. Now, less dense. Do you agree that less dense stuff could be warm air? And the more dense stuff would be cold air. So in this circulation, what do I actually have? I have warm air rising and cold air sinking. That circulation is called a thermally direct circulation. So I'm going to ask you on a test, what is a thermally direct circulation? And the answer is, it's when warm air rises and cold air sinks. What does a thermally direct circulation do? Well, it converts potential energy into kinetic energy. How? By lowering the center of mass. And that's what's going on. So let's take a thunderstorm. Do you recall from the very beginning, I said a thunderstorm is a process. It's warm air rising, cold air sinking. A thunderstorm is a thermally direct circulation. It's converting potential energy, in this case, CAPE, into kinetic energy. So when the thunderstorm forms, it gets windier. The thunderstorm stops, the winds will eventually die down. As friction slows it down, we have viscosity. And that lowers the center of mass. Now, how do I get the center of mass raised? Well, I could have taken this partition that I drew. I had that partition there. I could have taken that and actually spun it and forced the heavy more dense cold air up and let the warm air come down. But that would be me doing that. See, I provide the kinetic energy. So everything that you see here is backwards. Instead of potential converted to kinetic, I have kinetic energy going to potential. And instead of lowering the center of mass, I raise the center of mass. And instead of warm air rising and cold air sinking, I have warm air sinking and cold air rising. And that is not a thermally direct, that is a thermally indirect circulation. So get that clear. A thermally indirect circulation is when warm air rises, cold air sinks, and I convert kinetic into potential energy. The Ferrel cell, which is a mid-latitude cell, is this. That's the most common thermally indirect circulation. And that's what's going on. So almost everything in the atmosphere is converting potential into kinetic. Eventually things would stop because of viscosity. The question is, how do I replenish the potential energy of the atmosphere? And that's an important question. Well, replenishing the potential energy of the atmosphere says I have to raise the center of mass. So here's the question. What's the center of mass of the atmosphere? And now most people are going to say, well, is it the center of the Earth? Because they go, oh, the Earth is a sphere, and the atmosphere is this layer around it. And so what I'm saying is the center of mass of the atmosphere must be there. No, it doesn't work that way. You want to think of this as being a flat surface. You want to think of the atmosphere as being a huge box of air. Okay, there's the box of air. Now, when I'm standing here at the bottom of the box, how much air is above me? And the answer is all of it. When I'm standing above the box of the entire atmosphere, I've got how much air is above me? None of it. So the center of mass is I have half of the air. Well, when I'm at the ground, how much is all the air? Well, it's about 1,000 millibars. What is it when I have none? Well, 0 millibars. So what's half? And the answer is 500 millibars. So 500 millibars is the center of mass of the atmosphere. That's kind of important for you to know. Okay? Now, how do I lift? How do I get this center of mass to go up? Well, let's imagine that I have the center of mass of the atmosphere. I've got this layer. We've got this layer of air. Half the air. What if I heat that air? If I heat the air, won't the air expand? So basically, by heating the air, I'm going to cause the atmosphere to expand. And when the lowest half of the atmosphere expands, the center of the mass is raised. And that gives me potential energy. So what causes the atmosphere to get warmed up? Well, the ultimate source of potential energy of the atmosphere is the sun. And maybe I should make a yellow sun unless we're on a foreign alien planet where there might be a green sun. And the sun, just so you know, typically gives radiation which is transparent, and it goes primarily to the earth. Then there's three things that heat the atmosphere mostly. You have outgoing long-wave radiation that's absorbed by the atmosphere. That's known as the greenhouse effect. So that's OLR. And we also have an upward flux flow through an area of latent and sensible heat. So the fact that the ground, on average, heats the atmosphere, gives it water vapor that you can release in clouds, and you have outgoing long-wave radiation, that is what gives the Earth's atmosphere potential energy. Then thermally direct circulations come along and start converting that potential energy into kinetic energy, And the motion of air is what we call a circulation. If it's moving up and down, we call it convection. If it's moving horizontally, we call it advection. So we are moving the air because the sun heats the atmosphere. Then the atmosphere would eventually slow down because there's resistance, there's viscosity. As long as we have the sun, we'll replenish the potential energy. Potential gets converted to kinetic energy in thermally direct circulations, and that moves the air. And that's the way the universe works. And with that, I will see you guys later.